good morning, friends. We know that the carbon in alkenes is in sp2 hybridized form. That's why its tetravalency is maintained along with it is having two types of bonds. One is sigma covalent bond, another is pi covalent bond. Even in alkenes, carbon maintains its tetravalency. Today, we are going to deal about the preparation of alkenes. Alkenes, though obtained from fossil fuels, it can have its own limitations because fossil fuel is getting exhausted day by day. That's why we need to prepare the compounds in our laboratories or industrially it should be obtained in the bulk. The major methods of preparation of alkenes we will be dealing today. One of the foremost and most widely used method is reduction of alkynes. If I take alkynes which has triple bonds and we reduce by using a reducing agent, then it reduces to give alkenes. If I use a strongly reducing agent like hydrogen and platinum or hydrogen and palladium or hydrogen and nickel in the finely divided form, alkynes directly gets reduced to alkanes. And this type of reduction by using the catalyst in the with reacting with hydrogen, it is called as catalytic reduction. As we use the catalyst like hydrogen, the platinum, palladium, or nickel. Here also, for preparation of alkenes, we can use palladium charcoal catalyst as reducing agent. If at all I use palladium carbon, then it gives directly the alkanes. It's just palladium if I use directly. If I take alkynes and treat with palladium and hydrogen, it gives rise to alkanes. That's why we use palladium charcoal catalyst. This catalyst, that is palladium, when I treat with charcoal, it is partially deactivated. When this is partially deactivated, poisons are produced that are sulfur compounds or quinolines. Why we have to use partially deactivated catalyst? It's because of the fact that to reduce the activity of the palladium. If I reduce the reactivity of palladium or activity of palladium, it controls the reaction. It won't gets converted, alkynes won't get converted to alkanes. It stops at alkenes. There's something like that. If anyone are overactive, then we have to make them active. We have to give some tasks which are difficult to them. Then it's their activity gets reduced, and then they become active. We use this partially deactivated pelletized charcoal, and this pelletized charcoal was first used by Lindlar, and that's why this partially pelletized charcoal is named after him as Lindlar's catalyst. To control the reaction, We use this Lindlar's catalyst. It controls the formation of alkanes from alkynes. It stops the reaction at alkenes. We can also reduce the alkynes by using sodium and liquid ammonia. Reduction of alkynes to alkenes by using sodium and liquid ammonia was given by Birch, and that's why it is named after him as Birch reduction. We can obtain alkenes by reduction of alkynes by using two different catalysts. One is the Lindlar's catalyst, another is the Birch reduction. In Lindlar's catalyst, we use partially deactivated pelletized charcoal as a catalyst. In case of Birch reduction, we use sodium as the catalyst. Let us look into the reduction of alkynes and its reactions. I take a 2-butane. It has 4 carbons, and at the 2 position it has a triple bond. That's why it is called as 2-butane. And I treat with pelletized carbon, that is partially deactivated palladium and hydrogen, and heat it. The alkyne, the triple bond, at the across the triple bond, the hydrogen gets added up and it gives rise to alkenes, that is 2-butene. Another method of preparation of alkenes by alkynes is by using a more simpler reagent like sodium and liquid ammonia. It is given by Birch, that's why it is named as Birch reduction. In both the methods, we can obtain the same alkene. We can use Lindlar catalyst or we can use sodium and liquid ammonia. For reduction using palladium and carbon and hydrogen, this is an acetylene or any alkyne. We can use this reduction process by using a par hydrogenator, which had explained in the preparation of alkanes from alkenes. Another method of obtaining alkenes is dehydrohalogenation of alkyl halides. We can take alkyl halide. This alkyl halide may be alkyl bromide or alkyl iodide. The alkyl halide example is methyl bromide or methyl iodide. The simplest form, ethyl bromide or ethyl iodide. These bromides and iodides are treated with alcoholic potassium hydroxide. Alcoholic potassium hydroxide, generally we use is 10% potassium hydroxide solution. How will you prepare this 10% potassium hydroxide solution? We take potassium hydroxide and dissolve in alcohol. This is alcoholic potash. And this undergo elimination of hydrogen from the beta carbon. What is this beta carbon? The carbon which is next to the carbon to which halogen is attached. And the hydrogen from the beta carbon and halogen from the carbon to which halogen is attached are eliminated as hydrogen halide. That's why this reaction is named as beta elimination. Let us look into the reaction of beta elimination. I take ethyl halide. Halide is represented as X halogen, and this X may be either bromine or iodine. Why bromine or iodine? They are more easy living group. Why they are more easy living group? Because they are bulkier than other halogens. I take potassium hydroxide or alcoholic potash, that is potassium hydroxide. I dissolve in ethanol. The potassium hydroxide can dissociate into K plus and OH minus. As it is a strong base, OH minus abstract the hydrogen from the beta carbon. The alpha carbon is one into which the halogen is attached. This is the alpha carbon, and the hydrogen attached to the carbon which is adjacent to this alpha carbon is beta carbon. OH minus, it is a strong base. It abstracts the proton from the beta carbon. Once this hydrogen is abstracted as H plus, it leaves the electrons onto this carbon, and the excess electrons carbon are called as carbon ion. Carbon ion is formed as an intermediate. Carbon ion is electron rich, and that's why it is highly unstable. As it is unstable, it is more reactive. This excess electrons on this carbon is shared with the adjacent carbon. This adjacent carbon, that is alpha carbon, is electron deficient as it is attached with the halogen over here. This is electron deficient, this carbon, and this carbon is electron rich as it has gained the electrons by deprotonation, and this XLX electrons is shared with the electron deficient carbon. Already this carbon is having 4 atoms attached to it, and one more bond if it is found, it becomes unstable. That's why halogen gets removed with along with its electron pair, and I'll get alkene. This X minus combines with the potassium K plus, and it gives rise to potassium halide. If it is X is chlorine, potassium chloride. If it is bromine, potassium bromide. If it is iodine, it is potassium iodide. As I said, they generally the alkyl halide, the halide what we take is a bromide or a iodide, as they are more easily living groups. The rate of the reaction will be like this. If it is halogens, we take iodide preferably than bromides, preferably than chlorides, because iodine is more easy living group than bromine than chlorine. That's why the reactivity of the halogens is that iodides are more reactive than bromides are more reactive than chlorides. The alkyl group, tertiary alkyl halides are more reactive than secondary alkyl halides are more reactive than primary alkyl halides. We will deal with the mechanism of the reaction in when we deal with the elimination reaction in detail. The vicinal dihalides, if I take and dehalogenate it, we get alkenes. This is the third method of preparation of alkenes. What are vicinal dihalides? These are those carbon compounds in which it has two halogens. Dihalides means it has two halogens. Halogen groups attached to it, right? And this position of halogens is that it is at adjacent to each other. The two halogen atoms, when it is attached to the adjacent carbons, then it is called as vicinal dihalide. These vicinal dihalides is converted to alkenes when we heat it with zinc dust and ethyl alcohol. The example for vicinal dihalides is like this: CH2Cl and CH2Cl attached to each other, or CH2Br. X may be any halogen like chloride, bromine, iodine, or fluorine. When I treat with zinc dust and ethanol, and I'll get corresponding alkene. Let us look into the reaction mechanism, how this reaction occurs. And when this treated with zinc and ethanol, it eliminates as zinc halide. If it is X is bromine, I'll get zinc bromide as the byproduct. If it is iodine, I'll get zinc iodide as the byproduct. Generally, X should be bromine. We get zinc bromide as a byproduct. Another method of preparation of alkenes is taking alcohols and dehydrate it. This is also a beta elimination process. For dehydration, we use strong acids like that of concentrated sulfuric acid or concentrated orthophosphoric acid. In case of alkyl halides and dehydrohalogenating it, that is called as beta elimination and is more easy to occur because halogens are easy leaving group. But however, if I take alcohols, OH and the H from the beta carbon is eliminated, I'll get corresponding alkene. As we use a strong dehydrating agent like concentrated sulfuric acid and concentrated orthophosphoric acid and heated strongly at 443 Kelvin to get alkene, that is the dehydrated product of alcohol. As is name, dehydration, removal of water by using concentrated sulfuric acid and concentrated orthophosphoric acid and heating at very high temperatures. OH is not an easy living group like that of halogens. That's why we should use strong reaction conditions, high temperature, and strong reagents like concentrated sulfuric acid or concentrated orthophosphoric acid. It undergo dehydration in the presence of concentrated sulfuric acid, which is a dehydrating agent, and heat it at high temperature. I'll get alkene with the liberation of water. And let us, how is the mechanism? We will deal in the reactions when we go for alkyl halides preparation. There are four methods of preparation that are reduction of alkynes by using partially deactivated catalyst like Lindlar's catalyst or by Birch reduction, elimination of alkyl halides, that is dehydrohalogenation of alkyl halides. The third method is dehydration of alcohols. Fourth method is dehalogenation of vicinal dihalides. These are the four methods of preparation which is generally used for preparation of alkenes, the olefins. Let us look into the reactions of alkenes in the coming presentation. Till then, have a nice day.